So, hello, ladies and gentlemen, from both Hamburg and the San Francisco Bay Area in these still very special and challenging times. Welcome to today's broadcast on the topic Cells in Motion, how to optimize your shake flask and bioreactor cultures. Our webinar today will be presented to you by my colleagues Ines Hartmann and Ankita Desai. Both are amongst Eppendorf's most experienced application specialists in regards to supporting scientists with their suspension cell culture applications, and I will give you a short introduction about both in a minute. My name is Christian Haberland, Marketing Manager for Instruments and Systems at Eppendorf, and I will be your moderator for today's webinar. At the end of the presentation, I would like to give you a quick overview about solutions that might be helpful for you to improve your daily cell culture work. So let's go to some technical information before we start. Before we begin, I would like to encourage you all to get the most out of this webinar by submitting as many questions as you want at any time you want during the presentation. Simply type them into the Ask a Question box on the left and click Send. We will answer as many questions as we have time for at the end of the webinar. If you have trouble to see or hear the presentation, click on the Support tab at the top right or report your problem by clicking on the Ask a Question box on the left. Continuing education credits can be obtained by clicking on the tab at the top right and just following the process. So, and if you're interested in further resources, you can go also to the Resources tab by simply clicking on it. And you will also find that during the presentation, we have a few QR codes for you integrated that might lead you to, or will lead you to further content. All right. Now, let me shortly introduce the presenters of your webinar today. As I said, Ines Hartmann and Ankita Desai are amongst our most experienced application specialists focusing on suspension cell culture applications in shakers and bioreactors since years now. Ines Hartmann is application specialist cell handling, responsible for the shakers and mixers since many years now at Eppendorf in Hamburg in Germany. She joined the company 12 years ago and since then covered many cell culture related topics and obtained her diploma degree in biology at the Humboldt University in Berlin, here in Germany. And our second speaker, Ankita Desai, is a Bioprocess Field Application Specialist at Eppendorf in North America. She supports customers with her expertise in cell culture, bioprocessing, and related applications. After her master's in Pharmaceutical Sciences at the Northeastern University in Boston, she has gained several experiences working for global players in the pharmaceutical industry before she joined Eppendorf. And today we are happy that Ines and Ankita are going to share their knowledge with us. So I will stop talking now. Let's get started. Ines and Ankita, this stage is all yours.
Thank you very much, Christian. I would like to start. My name is Ines. Welcome also from the Northern Germany and from Ankita's side from the West Coast in the USA, California. And I would like to start to tell you what we have in the agenda for the next, let's say, 40 minutes. So first of all, we would like to tell you why shakers and bioreactors are used. Then we will have a short comparison of the two systems. And then probably the most interesting for you, we give you some tips on how to shake and stir cultures. And we will give you after that a short introduction also on feeding cells. So introduction to different process strategies. In the end, Christian, we will hand over to Christian again, and he will give you a bit more insights on the Eppendorf product solutions. So before we start, we have a first poll. We would like to know a bit about your experience. So Michelle, can you push out the poll? Okay. I see. Sorry, it was my fault now. So the question was, do you already work with shakers and bioreactors? And some of you use shakers, some of you use bioreactors, half-half, and some of you were very new to both systems. So I go back. That is good. So now we would like to tell you why these systems are used. So a broad range of cell types and organisms, from very simple ones, from bacteria, yeast, and fungi, for instance, to very complex plant cells, algae, insect cells, up to mammalian or even stem cells, are shaken or stirred in shakers or bioreactors. The importance in biotechnology industry is immense. So, of course, in pharmaceutical and life sciences, a very actual topic is the vaccines, of course, for corona. Therapeutic proteins, antibodies, up to emerging cell therapies and stem cells are produced in cells. Also, food and feed is an important topic. Here, beverages, everybody knows yeast, beer, feed additives, but also flavors and vitamins. For all that, you need to cultivate cultures in a shaker or in a bioreactor. Biofuels and chemicals, so we talk here about the important topic about sustainability, for instance, the replacement of the addition of biopolymers, for instance, or alternative fuels from algae, for instance, or platform chemicals. So for all this, you need to cultivate cells. But the question is, why using shakers and bioreactors? These systems are used to optimize, first, nutrient supply, second, to stabilize the temperature, and third, to make oxygen available to the cells. So shaking or stirring in general means culture improvement. So let's go to the first point, nutrient supply. Just an easy example of a shake flask. On the left-hand side, you see a static culture. When there is no shaking, you have sedimentation and, worst case, a gradient formation. So there is a limited and inhomogeneous access to nutrients for the cells. So that means inhomogeneous and low cell yields. When you start shaking or stirring, so moving the liquid, the suspension will be uniformly distributed and you have an improved and homogeneous access to nutrients. The second point, also very important, we did not ask that, but I think most of you apply temperature to the system, either by having an incubated shaker, having an open-air shaker in a temperature-controlled room, or using a temperature control for bioreactors as well. Temperature is an important factor as well, either first for cell expansion or second to have the optimum for the product you would like to produce in the cultures or from the cultures. Let's have a look at cell expansion. So each culture has its optimum. So when we culture, for instance, let's take simply E. coli, at its optimum around 37, 35 degrees, we have a nice exponential growth curve. But if we have higher temperatures or even lower, then we have a slowed growth. That is sometimes beneficial. A slow growth is beneficial often for the production of therapeutic protein expression. It improves solubility of the protein by slowing down the culture's processes. Also, the protein is produced slower. Plus, also, it reduces the degradation of proteolytically sensitive proteins. Third, probably the most important thing why shakers and bioreactors are used is the oxygen availability. Oxygen is one of the main influencing factors on aerobic cell growth. So except for some anaerobic cultures where it's not important, this is the limiting factor often in shakers and bioreactors. Oxygen is a key substrate for growth, production, and maintenance activities. And cells cannot obtain oxygen from the air in a non-compound form. They need it as dissolved oxygen in the media, so in compound format. So the problem is when you culture the cells in the media, it has a low solubility in the liquid. So let's have a look. Between the gas phase and the liquid phase, you have your cell in the media, of course, here, for instance, E. coli, and you have oxygen in the gas phase. Oxygen must pass to the liquid phase, and then you have it in a compound format, but you have a constant concentration drop. And until it reaches the cell, you have another drop. So what shakers and stirrers do is they increase the oxygen transfers, but both have different strategies. So let's have a look. A shake flask, very simple. You have a flask and a cap, and oxygen passes by diffusion. This should be oxygen in the air. And you have only a still surface here, so no shaking. That is a small surface. So the oxygen transfer, the surface for oxygen transfer is relatively low. When you have shaking, you have a constantly formed swirl building up, and that means also that you have a larger surface. A larger surface means a higher oxygen transfer to the culture. And this swirl is constantly moving around and giving new oxygen to the culture. Depending on the RPM, you can adjust this swirl, of course. And this is one factor to increase oxygen transfer. So for shakers, it is the available surface area for diffusion of oxygen into the media and broth what is improved. So Ankita, how is it in bioreactors?
Thank you, Ines. In a typical bioreactor, which is a stirred tank vessel, you have a sparger, which can be either open pipe sparger, ring sparger, or an L-shaped sparger, depending on the type of application or the process needs, which is also accompanied by an impeller for agitation. So depending on the constant feedback from a DO sensor, air or pure oxygen can be actively pumped into the culture via the sparger, which causes a creation of gas bubbles in the bioreactor. And stirring allows proper mixing of this culture and improves oxygenation by evenly dispersing these gas bubbles in the culture. So this provides a large surface area for oxygen transfer from gas phase to the liquid phase. Back to you, Ines.
Thanks, Ankita. There are two terms that you should know when you talk about oxygen transfer, and also two terms you can measure in the culture. We talk here about the terms OTR and OUR. So what is it? Again, this picture, the gas and the liquid phase, could be a bioreactor or a shaker with a media in it. So we have either bacteria or you cultivate mammalian cells, please not in one tank, otherwise the bacteria would overgrow the mammalian cells. The OTR means oxygen transfer rate. That means the rate at which oxygen gas is transferred from the air to the liquid over a given period of time. And this can be measured. Then we have the OUR, so the oxygen uptake rate, and this is the rate at which the cells consume oxygen over time. So this you can measure as well. In generally or simplified, one can say that the oxygen transfer rate, so the OTR, is the limiting factor, and the OTR defines the maximum cell density. So this is the more important thing to talk about, because the cell's oxygen uptake depends on the OTR. Let us have a look in a shake flask to maybe a bit better explain what happens with the oxygen and what is OTR and OUR influence. So here you agitate a culture, you have a temperature, and E. coli, again, let's take it as example, is growing nicely, exponentially growth. The oxygen uptake rate, in accordance with that, also the OUR, so the oxygen uptake rate in the cell goes up. whereas you see here, the liquid's oxygen decreases because of that. Because the cell is taking oxygen up, decrease in the liquid occurs. But of course, this is not meaning, because of shaking and steering, there is always introduced new oxygen into the culture. So in best case, there is a balance between oxygen introduction and oxygen uptake. And this you can control with agitation, fill, aeration, and other parameters with shakers and bioreactor. Now let's talk a bit about math, very shortly only, and I would like to hand over to our Bioprocess Application Specialist, Ankita, again.
Thanks, Ines. So this slide describes how OTR can actually be calculated. So just to give a snapshot, KLA, which is the volumetric mass transfer coefficient, actually describes the maximum oxygen transfer that can be achieved in a system within a given set of operating conditions. So the driving force for this transfer of oxygen from the gas phase to the liquid phase is actually the gradient between the concentration of oxygen at the interface and that in the bulk liquid. So essentially, when an equilibrium is reached, there is no more oxygen transfer from gas to liquid phase, and the OTR would then become zero. For typical bacterial and yeast cultures, the critical oxygen concentration is usually 10 to 50% of air saturation. So above that critical level, the oxygen concentration no longer limits the cell growth. So in order to have an optimum growth, it is important to maintain DO levels above the critical value by sparging the bioreactor with air or pure oxygen. So like we saw in the previous slide, during those initial days in culture, when the cell density is low, the OUR is less than OTR. But as the cells start multiplying and reach higher cell densities, it is important to maintain OTR values which are equal or exceeding the OUR of the growing cells. So in this graph, we also have a KLA profile of BioBlue 3C macrosparge vessels at different tip speeds. Essentially, maintaining a constant KLA between different vessels of different sizes is one of the most commonly used strategies for cell culture scale-up. Since in this case, KLA or OTR could very well be the limiting factor which would then control the growth rate of your cells. So let's talk a little bit more about the KLA. So KLA is the volumetric mass transfer coefficient, which is a measurement of the capacity of the bioreactor to transfer oxygen into the culture under a given set of operating conditions. So when we're talking about the scale-up of bioreactors, KLA is a term which is heard very often. A very common scale-up strategy is to select equipment of different sizes which have similar KLA capabilities, so that processes at a small scale R&D equipment can be successfully replicated at larger production scale systems. A typical KLA-based scale-up can be performed by maintaining constant KLA values among different vessels, providing flexibility to then accommodate different types of cell lines. Here we just have some of the factors which affect KLA in both shakers as well as bioreactors. So there could be some equipment-specific parameters like the vessel geometry, stirrer type, installation conditions. Some process parameters like agitation rate, filling, aeration rate, type of gassing device or the sparger, as well as pressure. And it also depends on the properties of the liquid medium, meaning the density, viscosity, surface tension, as well as coalescence properties.
Thank you.
Here, go ahead, Ines.
Yeah, we have some support material also for you. So if you want to know more how to measure oxygen transfer rate, for instance, in bioreactors and fermentation vessels, it will be online soon. So check the Eppendorf website. If you would like to have it now, please drop us an email, bioprocess-experts@eppendorf.com, or just via lab routes. For Shake Flask, there is also online, for instance, a KLA calculator, so you can also calculate the KLA by this, and you type in just in this if you check the QR code here, you go to the website, you can type in the shake flask size, fill volume, RPM, and you can determine, it gives you the KLA, so the aeration efficiency of the system with the parameters you apply, which is for the shaker, the RPM, flask, and fill volume averagely. Okay, so now we come already to the next chapter, so a short comparison of the system. So what are the differences? What are the similarities? And here we have also a short question for you. And the question is, what are your working volumes? So Michelle, please drop the question up. So with what volumes do you work in your daily lab routine with shakers and bioreactors? Okay, I see anything between 50 and 2 liter. Okay, so it varies. So let us compare the systems. So here, the first difference is, of course, a shaker, you have a lower invest than for a bioreactor, so it's relatively low, and shake flasks are not as expensive, even though a single-use vessel could have its price as well. Bioreactors mean a larger invest. Technical expertise for a shaker, you don't need it. Maybe there are some things to consider, but it's everybody can use a shaker, whereas a bioreactor needs a certain kind of technical expertise because it's more complex. For the working volumes and the experimental throughput you can achieve with these systems, let's first have a look at the working volumes. With a shaker, you can go up maximum depending on what flask size you use, and there are different flasks where you can also achieve higher fill volumes with special designs. We come later to it. So let's say 2 liter per flask, and down if you use, for instance, plates, down to 1 milliliter. Or even lower, 500, 200 microliter is okay in a Deepwell plate to use. For bioreactors, you cannot go so low, but you can start with I think 350 around milliliter, but you can scale up, of course, to production yields 2,000 liter. The throughput also is vice versa. If you, for instance, use plates, you have 96 wells in a 96 well plate, as the name said. And if you have, for instance, a triple stack of a shaker, you can cultivate in parallel more than 7,000 cultures. For bioreactors, it's low to medium. So in parallel, with a mini bioreactor system, parallel system, it's 24 and lower. So, but shakers and bioreactors team up very well. So I give over to Ankita to explain shortly the workflow.
Thank you, Ines. So here we have a typical scale-up workflow in this slide. So while the main goal of a scale-up process or scaling up your process is to ensure large-scale production of the product, all the while maintaining the desired product qualities and characteristics that are obtained at the small scale. To this end, we start with the small-scale experiments in shake flasks to provide the initial cell growth data and provide seed cultures. Screening can be performed then starting with mini bioreactors, which would provide small-scale solutions at an R&D scale, including media design or optimization of different parameters. Next up would be our bench scale systems, which provide a great tool for process development and technology transfer to eventually scale the process up all the way to pilot or production scale systems. Back to Ines.
Yes. We saw already at the first part that the liquid movement is different, and we get to it in the next chapter a bit more. Shakers have an orbital shaking movement. I will tell you in the next chapter a bit about this. And bioreactors have a stirred tank principle, so with a stirrer and introducing oxygen by bubble formation. Concerning process control and process monitoring, of course, for bioreactors is broad and flexible. For shakers, it's agitation, and you can control chamber conditions we see on the next slide. What you can control and process monitoring, there are options. You can add instruments to the shaker, for instance, sensors. So the basic process control in shakers, you have different shaker types you can decide for. For instance, open air, the very simplest one, if you have a temperature-controlled room that offers the control of agitation. Then you have the most important shakers, incubated and incubator CO2 shakers, depending if you have the CO2 from mammalian cells, where you have CO2 and humidity control, and of course temperature control. And then you have the incubated shakers, which offer temperature control plus also refrigeration, and optionally for algae or other photosynthetic organism, you can add optionally photosynthetic lights. Process control, just for what you can do in incubated shakers, you can also, at least in our shape, operate with a program, so you can add several steps. For instance, meaning the easiest thing just to understand, step 1 would be growing at the cell's optimum, 37 degrees. And 250 RPM, and then maybe it's weekend and you want to store the culture safely at cool temperature, so you can stop the curve with setting 4 degrees or 10 degrees with even off or low shaking. So you can come Monday morning in the lab and you have you can control the growth curve, and you can do also different programming types if you have photosynthetic lights, for instance, circadian rhythms, etc. You can add accessories. For instance, there are companies offering in Flask feeding if you want, or there are companies offering in Flask monitoring. They are, of course, also compatible with our system. They are compatible with all shakers. You can monitor, for instance, biomass and pH, or also DO. There is, for instance, also that company, Aquila, or Presense is another company. Yes. Yes, with this I would like to hand over to Ankita, because a bioreactor is more than a vessel.
Thank you, Ines. So here, what I'll be talking about is a basic bioreactor control and the flexibility that it offers. So a bioreactor itself is more than a vessel. So here we just have a little cartoon where bioreactor is essentially compared to a fish tank, so to speak, wherein the tank itself is the bioreactor vessel which houses the culture, which is also called a vessel. We also have the water, which is compared to the medium for cell growth. We have fish, which are compared to the cells growing in the fish tank. We have agitation going on in the vessel, which is going to be done via the agitator and agitation shaft, as well as the impellers. The fish food, or the glucose, amino acid, various nutrient substrates that are going to be added to the culture. We have the product of interest, which is going to be secreted. We have temperature, dissolved oxygen, as well as pH control going on inside the vessel. So the main idea is that by controlling the different input parameters like temperature, pH, dissolved oxygen, agitation, nutrients, etc., we are able to influence the output variables like the desired product yield and cell growth. Bioreactors offer active monitoring and control of various parameters, just like temperature, pH, DO, agitation. There is also active control as well as monitoring of these parameters using feedback obtained from the sensors in the vessels. You are able to implement different feed strategies like a fed batch, continuous, or perfusion culture processes that can be done using the controller capabilities. Also, because of the varied sizes available, stirred tank bioreactors also provide an ideal platform for scale-up or scale-down approaches. Bioreactors have different components which make it all the more flexible to use depending on the application or your process requirements. So these are just some of the components that a bioreactor is equipped with, and of course that will change based on your process needs. So for example, agitation is controlled by motor and the impellers that you choose. Aeration will be controlled by the gases flowing through the sparger, again based on the feedback obtained by different sensors like DO and pH. Temperature is controlled by either heating using the heat blankets or water jackets and cooling fingers based on the feedback provided by the temperature sensor. In addition to these, the controller systems are equipped for integration to third-party equipment or sensors like turbidity or OD sensors, among others, or even peristaltic pumps to enable automated feeds during the run. Back to you, Ines.
Thank you, Upsala. So we went already through why using shakers in bioreactors, and we gave you a comparison of the system. And now it's time to give you some tips on how to shake and stir cultures. First of all, we have now the last poll for you to know a bit about what are your concerns in your cultivation. If you tap, if you have some of these problems, please. Ah, okay. No problems. Oh no, it's sorry. Okay. Contamination seems to be an issue. Shear sensitivity. Oxygen limitation. Yes. So, and also some of you have no problems. That is also good. Keep fingers crossed that it stays like that. You do everything right. So let us see how to shake and stir cultures. The challenges in shaken and stir cultures are manifold, depending on the system you use, on the culture of the clone you use. Oxygen limitations is a big one. Evaporation, if we go down to plates or very small volumes or long cultivation times, for instance. Viscosity, for instance, if some of you do fungal cells or cultivate fungi. Shear sensitivity, we talk here about more mammalian cells where you apply low RPMs, and contamination sensitivity would also be more with mammalian cells. So we divided here the chapters. So first, let's have a look on the shakers. So what are influencing factors when you use shakers, or what set screws you can adjust? So the influence on oxygen supply and the set screws are the vessel type, the fill volume. The fill volume we advise to use not more than 20%. If you talk to bioprocess people, and in this area they even go down to 10%. When it's about mammalian cells, it's not that sensitive. You can go up to a bit higher volumes, and also here we have different specialized Flask companies, for instance, where you can go up to higher volumes. On the shaker side, you have the shaking diameter. I will explain it a bit after this slide, and the RPM, of course. So these are the 4 set screws. So again, we talked about in the beginning, you have the, so what is the orbit of a shaker? Maybe you have heard of it. Another name is the shaking diameter. So let's simply take here an open air shaker with a not as well drawing here, and you have the flasks on top of the shaker, usually in a clamp or on a sticky pad, and they are rotating. And this rotational motion is called orbital motion, so circular motion, and by the direction of by the centrifugal forces, you have this swirl building up in the shake flask. And by this, you have the introduction of the oxygen. So this diameter here, by which the shaker is moving the platform around the circle, is the shaking diameter or orbit. You will encounter different suppliers, and different kind of shakers have different orbits, so different diameters, from small to very large. And instruments, when you have instruments, usually a very small orbit is paired with a very high max speed. It's like, if you know, from centrifuges. You cannot have a very high speed and a very large orbit, because it would just be too much power input for the device. So let's take a mixer. A mixer has a very small orbit. This is our thermomixer. It is a 3 millimeter orbit. But you can set a rotational agitation of up to 3000 RPM. This device is perfectly suited for small diameters. For instance, plates, tubes. So here you see the curl, for instance, in a Deepwell plate is nicely mixed. So it's more, we talk here about mixing. A shaker, what you find usually is a 50 millimeter orbit, and this can be agitated up to 300 RPM, and a 25 millimeter orbit, which is a bit higher, up to 400 RPM. By the way, when you stack shakers, always put the higher orbit on the ground. The relationship between RPM and the shaking diameter. Both have an influence on the oxygen introduction. Here you have, let's say, a smaller orbit, the 25 shaking diameter, and when you move to another shaker with a 50 millimeter orbit, this will mean that you have a better aeration, a higher OTR maximum, let's say. So here you see a bigger wave. A bigger wave, remember from the beginning, you have a larger surface and more oxygen entering the liquid. So doubling the orbit size will double the OTR. The speed as well. If you have 100 RPM, you nearly shake it. But for sensitive cells, it's maybe good. For E. coli, you go on a very high RPM, 200, 300, even 400 or 500 you can set. And a higher RPM means a better aeration as well. But also it means more mechanical shear forces. So yes, we often get the question, what orbit should I take for what? So the 25 millimeter is like, let's say, the universal orbit. You have conicals, or let's say tubes, tube bioreactors, Flask, in the range from 25 to 2 liter. When you only have, for instance, very large flask, larger than 2 liter, or shear sensitive cells, or also plates, then a 50 millimeter is beneficial. For plates, also a 3 millimeter. If you have a mixer with a plate adapter, works also quite well. That was the shaker. Let's have a look at the shake vessels. A diversity or a big variety of vessel designs exists, and suppliers make their best to create new formats with adding aids to help to increase the aeration. So well designs are different and optimized. You have tubes with a conical button, and here, for instance, the baffles, we come to it in the next slide, and maybe some of you use also the Fernbach design. And this is, you remember from the beginning, the surface area for oxygen transfer in the Fernbach design is very much enlarged because you have just a wider flask. This is, I think, very good to understand. So these two, the baffles and Fernbach designs, are designs to improve aeration. Let's look a bit deeper. Before you have to make the decision, and now we come also to the contamination prevention topic, to use glass or plastic. Glass is the traditionally used material. It is cheap. You can reuse it, and for flasks, cleaning is not so much of an issue. Autoclave it. Also, if you have, for instance, bacteria culture, which have a problem with oxygen limitation problems, it supports also. Glass is hydrophilic, the liquid is hydrophilic, and imagine you have this curl, the swirling around the flask, and hydrophilic likes hydrophilic, as you remember, so it curls up the sides, and this means an enlargement of the surface, and you see here on the right side, maybe a bit small, the hydrophobic flask, the hydrophilic flask, the red one is higher, so you have a better oxygen transfer. The risk contamination, of course, is higher. On the market, of course, when we go to pharmaceutical or product safety, the trend is to going to plastic. There is, of course, a minimized risk of contamination. There are diverse materials here in the center, so a bit milky flask is polypropylene for bacteria, polycarbonate, or there are other plastics because of the leachable topic, or mammalian cells are quite sensitive. There are different plastic types. You hear polycarbonate is used more for mammalian cells, and you see it's as clear as the one on the left side as glass. You have also, it comes mostly with sterility at a certain sterility assurance level, and if the vented filter cap is with the vented caps are usually have a 0.2 micrometer filter in it. Yes. Now we come to the baffled and the non-baffled flask, and the trick or the aeration improvement is here by having some kind of defined cavities in the bottom, as you see here. So, and for instance, if you shake E. coli in normal LB culture at 150 RPM, so not as high, you see that the baffled culture has a faster growth. So it is definitely beneficial to use when you only can apply lower speeds, or if you use higher fill volumes, or also with viscose liquids. So fungi cultures or other viscose cultures, the baffles are beneficial to use. One problem with the baffles, as you see here, I don't know if you see it probably, the right one, you have foam formation, and you see it's a bit more turbulent. But that is no problem because there are a lot of anti-foam solutions in the market. You add a couple of microliter, and that then the foam vanishes, because at lower speed it's not such a problem, but at high speeds the foam can hinder the oxygen from passing the air to liquid barrier, let's say. The last topic about shaking vessels is a very small volumes, Deepwell plates. There the issue are sedimentation. And here is the tip: reduce fill volumes if you note any sedimentation curves. So it's always beneficial to do growth curves in the beginning with maybe different fills. And we noted good settings that you just take either depending on the orbit, you have 50 millimeter with 300 RPM, 25 with 400, or if you have a thermomixer with 1000 RPM. And then you will have a good growth. And if you have still sedimentation, then you can reduce the fill. Here, for instance, is 500 microliter. Took also 1 milliliter works well. And evaporation is another problem. So here, just a tip: if you use a sealing film, you see it's a gray here. You have more evaporation if you have long cultivation times. There are special clamps, for instance, which can reduce evaporation available. So with this, I think we have a handling website. So if you have your phone ready, please check the QR code, and I would hand over to my colleague Ankita to tell you a bit about the bioreactor configuration.
Thank you, Ines. So talking about the proper bioreactor configuration, selection of an ideal bioreactor and a controller system will depend on the type of culture or application, as well as the process needs and requirements, which will influence aeration, mixing and impeller type, the different types of sensors or the tools that are going to be used in the process. So in the next few slides, we are going to dive into more details on some of these critical features that should be considered for selecting the appropriate bioreactor for any process. So the first factor that we'll talk about, which needs to be considered while selecting a bioreactor, is the material of our vessel, glass versus single-use bioreactors. A typical glass vessel consists of a glass body with a stainless steel headplate, which is used to connect different sensors, tubings, impeller shaft with the impellers, and other components in the bioreactor. Now, glass vessels have been traditionally used in the industry as they are autoclavable, and leachables are not an issue when you're using glass vessels. However, single-use vessels provide high product safety since the entire vessel has been pre-assembled, so there is no risk of cross-contamination. You have non-invasive DO and pH sleeves in these vessels, which further help reduce contamination risks as the headplate integrity is maintained and not user-dependent. Here is a quick flowchart comparing the workflows when using glass versus single-use vessels. Substituting the traditional glass bioreactors with single-use equipment can greatly simplify the bioprocess workflow. Single-use process eliminates the need for cleaning as well as autoclaving. This reduces the time needed to prepare the bioprocess run and lowers the contamination risk. Since these vessels are pre-sterilized, all you would have to do is connect the vessel to the controller and fill it up with media to prep for calibrations. Another big advantage, especially at larger bend scales, is the lower weight of the plastic vessels compared to glass, thereby reducing occupational hazards associated with overweight handling, thereby making this more ergonomic. The next critical component of a bioreactor is the impeller selection. So you can see here how different types of impellers cause different flow of the medium in the vessel. Radial flow occurs when the fluid is pushed away from the impeller's axis towards the vessel wall. Axial flow occurs when fluid is pushed up or down along the axis or the shaft of the impeller. So the orientation of an impeller, whether it's a left or a right-handed, and its agitating direction will determine whether the direction of axial flow is up or down. A typical Rushton impeller causes radial flow, whereas pitch blade impeller causes a combination of both radial and axial flow. So we'll talk a little bit more about these impellers in the next slide. So Rushton impellers are usually flat-bladed impellers. Their blades are flat and set vertically along the agitation shaft, which produces a unidirectional radial flow. Rushton and Rushton type impellers can commonly be used in fermentation of cell lines that are not considered shear sensitive, including yeast, bacteria, and some fungi, as they help achieve high OTR and high shear. The blades on pitch blade impellers are flat and set at a 45 degrees angles, which produces a simultaneous axial and radial flow. This combination provides better overall mixing and creates a high OTR compared to the unidirectional marine blade impellers. So pitch blade impellers are low shear impellers designed to gently mix the contents of a culture without causing cell damage. And they are most commonly used with mammalian cell lines or cell lines which are grown in suspension or even with the aid of microcarriers. And then we have the marine impeller, which produces the axial flow. So like the pitch blade impeller, the marine impellers are used for applications that require gentle mixing. However, due to the unidirectional flow, the KLA values of marine blade impellers tend to slightly be lower than those of the pitch blade. Now let's talk a little bit about some of the process controls that the bioreactors offer. Bioreactors are equipped with a DO as well as a pH sensor, which are constantly reading the culture conditions in terms of the percentage of DO as well as the pH of the culture. These sensors are constantly sending an input back to the controller system, and based on the feedback that the controller receives from these sensors, it initiates a response to ensure that the DO and pH are maintained at the desired set point. So for example, for a typical pH control, By the feedback response, the controller is trying to maintain the pH at a set point by involving the flow of acid or carbon dioxide as well as the base as required. Here is an example of a typical DO cascade for fermentation, wherein agitation, gas flow rate, as well as oxygen or pure oxygen are used to control DO at the desired set point. If you look closely at this graph, you can see that as the DO output percentage increases, which means that the DO percentage is drifting below the set point, the controller makes attempts to eliminate this drift. So the first step that will happen is the ramping up of agitation, followed by adding the gas flow rate increase, and then finally by introducing the pure O2 sparging. In a typical cell culture run, the agitation often stays constant because the cells are usually shear sensitive, and you only use air as well as your pure oxygen to control DO. Many other process parameters can also be monitored and controlled by simply integrating different sensor types with your bioreactor system. So for example, you have biomass readers like OD probes or turbidity sensors, metabolite analyzers for reading glucose, lactate, and other products. You have exhaust analyzers, which are constantly giving OTR, CTR, RQ readings, redox sensors, as well as options to include sensors from which allow for multiple measurements like an HPLC, NMR, or CDEX, or Agilent Technologies, or Nova Biomedical products. Let's talk a little bit more about the feeding strategies in bioreactors. So the first one that I'm going to talk about is the cultivation strategy, which is the batch fermentation. This strategy was used in one of our application notes to describe an E. coli growth in culture. The slide describes a batch fermentation mode where cells are seeded in a bioreactor and the nutrients are gradually consumed, all the while metabolites continue to accumulate, which is similar a little bit to the shake flask culture. So over time, the culture environment changes, wherein the nutrients are completely depleted and the byproducts accumulate, which eventually causes the cells to move into a stationary or death phase. So the maximum OD obtained in this run was about 77. Here you can see a typical growth curve, which is divided into the lag phase, stationary phase, and eventually the death phase, where the cell density and viability drops. And of course, you have the exponential phase here. In the next slide, I'm going to talk about a fed batch run. In this strategy, once the cells are seeded into the fermenters, they are allowed to grow as a batch culture until nutrients are consumed, as can be seen by this drop of glucose concentration around day 5 or 6 in this graph here. At this point, fresh nutrients are then added in increments throughout the remainder of the run to consistently maintain the nutrient concentration in culture, which you can see by the jump in the oxygen concentration starting day 7. However, metabolites like ammonium constantly accumulate in a fed batch culture, which could eventually become a limiting factor in cell growth. Using this technique, the exponential growth phase as well as the stationary phase can be extended to achieve higher ODs compared to a simple batch culture. So for example, in this study, an OD of about 240 was obtained compared to just the OD of 77 in a batch culture, which we saw in the previous slide. The third feeding strategy is a continuous fermentation mode. So as you can see in the picture here, in a continuous fermentation process, fresh media is being constantly added to the fermenter at the same rate at which used media and cells are simultaneously being harvested from the reactor. Thereby, there is a constant supply of fresh nutrients for the cells, and the toxic metabolites are being constantly removed from the culture. So as the rate of addition of fresh media is the same as the rate of removal of spent media and cells, the culture volume remains constant throughout the run. And an OD of about 159 was obtained at about 10.5 hours in culture here. Please feel free to refer to this app note that we have if for more information on these feeding strategies, and you can also use the QR code to access it. Back to Christian.
So thank you, Ines and Ankita, for this great presentation. As I promised you in the beginning, and before we will start with the last poll on the Q&A session, I promised to give you a little product insight into helpful solutions for your daily work. And I would like to show you a few shakers here and also some bioreactor solutions. And I would like to start with the Innova S44i incubated shaker, which you can see here. And with that incubator shaker, you can achieve higher flask capacity, which you can see in the graph here. So whatever type of vessel you will use, you will find a high flask capacity in the Innova 44. And you can check out also the comparison for the vessel type you're normally using. You can also shake faster for high yield protocols. So even in a stack, you achieve a high shaking speeds to really be ready for high yield protocols with specialized flasks. And you can see here in that little picture also that the shaker includes reliable shaking with high loads 24/7 with this new Eppendorf X drive, which has 5 eccentric shafts and 4 peripheral that really supports the load in the periphery of the platform. And if you want more information, you can go to eppendorf.com/S44i. The next thing I would like to show you is the CO2 incubator shaker New Brunswick S41i, which you can see here, which includes on the bottom part a shaking part, and also you can include a static shell for static incubation. Since this is based on Eppendorf CO2 incubator technology, it also includes 120 degrees disinfection here. There's no fan inside, so you have a smooth chamber that you can use, so a high capacity, and you also don't have to worry about those fan-containing boxes here and how to clean them. So together with the high temperature disinfection, it's really easy to provide high contamination prevention here. And it also, because you have 2 doors here, one inner and one outer doors, according to the CO2 incubator setup, you have significantly reduced gas consumption, which you can see here on this little slide here. And also, what customers always say, it comes with very quiet operation. If you're interested in more, eppendorf.com/S41i. Now, here comes the DustBox Mini Bioreactor system, which features 4-fold units for parallel processing. It supports process development following the QDB approach. And there's also integration of third-party analyze and DOE tools. You can check out the whole system under eppendorf.com/DustBox. It can be extended to 24 parallel operated bioreactors, and it comes with a working volume of 60 to 250 milliliters. And currently new is the BioBlue 0.3 SC 8-blade impeller system, which is specially designed for stem cell processes. And the last one is the latest bioreactor system from Eppendorf called Cyvario Twin. It's the next generation bioreactor control system, which you can see here, which features 19 different vessel variants, glass and BioBlue single-use vessels, and specially designed for stem cell culture and fermentation applications. It offers you increased flexibility and advanced application efficiency. And if you want to know more about the Cyvario Twin here, go to eppendorf.com/Cyvario. All right, so let's come to our last poll question here so we can keep improving our webinars for you. So the question is, how do you rate the content of today's webinar? We highly appreciate your feedback to really improve here. So I hope the survey and the poll gets pushed out. So we have at least some minutes left for a Q&A session. So if you have any questions you would like to ask Ines or Ankita, please do so. Just click on the Ask a Question box located on the far left of your screen, and we will answer as many of your questions as we have time left for, which is not much, but keep in mind that we will answer, or Ankita and Ines will answer all of your questions, so nothing is lost. And I see there are some questions coming in. I think I will start with the first one. I'll check this out. And so we have one question. I don't know who's going to get this here. How many different sensors can be integrated into one bioreactor vessel? So I guess that's for Ankita.
Yes, thank you, Christian. That is a good question, actually. That depends on the size of the vessel and the head plate. So, of course, you have typical or basic parameters like DO sensor as well as pH sensor, which will need to be measured during your run. Other than that, you also have biomass readers that can be incorporated, like an OD sensor for typical fermentation runs, or capacitance probe, which are also used for biomass readings. You can also have a redox sensor included in the run depending on your type of application, as well as glucose sensors that can be included. So I think that answer kind of depends on your type of application or the cell type that you're running.
Thank you, Ankita. Here comes another interesting one. The question is it possible to measure the KLA in a shake flask? That probably goes to Ines.
Yes, that's me. So measuring the KLA, so the aeration efficiency in a shake flask, yes, that is possible. It is less common because it's just due to lack of equipment or lab facilities, because the two methods applied are the gassing out method, which needs nitrogen gassing, and this is not very often available with the shaker. And the second method, sulfide depletion method, yes, you can apply, and it is beneficial also to measure the KLA in shakers, especially in bioprocess development, if you would like to compare the KLAs between the different systems. Shaker bioreactor is, for instance, one topic, and to verify the settings and the optimal culture conditions. And as said, you can there are available for shake flask oxygen sensors and so on. So it is for sure also possible and recommendable to measure the KLA in shake flasks.
All right, thank you, Ines. Okay, I think we are pretty short on time, but I think we have time for one more last question, so I have to choose wisely. Oh, this is an interesting one. So the question is, I have problems with foaming in the fermenter. So do you have any recommendations, Ankita?
Thank you, Christian. Foaming in a fermenter is actually a very common observation, coupled with sparging and agitation. Creation of gas bubbles during sparging can actually lead to foaming. So there's absolutely something that you can do to mitigate this issue. So there are various anti-foam agents available that you can use to mitigate this foaming issue. If you add just a few microliters of these anti-foam agents, that will help the foam subside and will prevent any issues from further forming. Absolutely.
Thank you, Ankita, for this, and also Ines for this short Q&A session. As I said, please send your questions if you have any to both of them, and we will answer all of the questions. So thank you again, Ines and Ankita. Do you have any final comments for our audience?
No, thank you. It was nice for us as well. Yes.
Well, thank
you for listening.
Attending.
Thank you for attending. See you next time, hopefully, when it's about stirring and shaking.
Okay, before we go, I would like to thank you all for joining us today and for your interesting questions. Questions we did not have time for, and those you have submitted during the on-demand period will be addressed by the speakers via the contact information you provided. And I would like to thank Ines and Ankita for their time today. and their very nice presentation. We would also like to thank Michelle Ashton and the LabRoots team for supporting us today. And this webcast can be viewed on demand. LabRoots will alert you via the email when it's available for replay. And we encourage you all to share this email with your colleagues who may have missed this live event today. So we say goodbye from Hamburg and from San Francisco Bay today. Have a nice day. And most importantly, stay happy, healthy, and help to protect others. Thank you and goodbye.
Goodbye. See you next time.
Goodbye.